In the previous video, we started to consider a situation in which a two-level system with the ground and excited state has a finite lifetime of the excited state. So the excited state de-excites with some relaxation rate, which we would describe as, which we would call KGE, and this process leads to an occurrence of evolution superoperator element UGGEE, which basically takes the population of the excited state, which is described by an element of the reduced density matrix rho EE, and brings it to the ground state. So this process basically empties the excited state and fills the ground state. So we found in the previous video how this element can be written. We have actually two formulations. One of them would be within our approximations the result for this, this would look 1 minus e to the power of minus k GET. But we also have a more general expression which considers a general evolution of the excited state. That is, we are basically in this situation writing the process of transfer from E to the G in terms of an integration over the evolution of the excited state, and then it looks like this, where basically the UEEEE gives a conditional probability that we will find the system in the excited state, and at every infinitesimal interval of time of the length d tau, the probability of jumping to the ground state is KGE d tau. So this is what we can now use for a construction of Liouville pathways that correspond to this process. Now this is very important because we have two Liouville pathways that go through the excited state in our four pathways description of the two-level system. I will start to write these Liouville pathways that go through the excited state. We have a rephasing pathway which starts by exciting the right-hand side of the diagram, and the second step is the excitation of the left-hand side. So we have, after two interactions with the laser pulse, that is after let's say the pump of our experiment, we have the system in the excited state. And now we know that when we assume the evolution according to the UEEEET, this thing will basically decay. So the contribution of the original pathway that we have here will decay, and that sort of dynamics, or that population which jumped to the ground state, will now have to act differently in the nonlinear response. It's clear that when I by pump excite the excited state, and then the excited state gets depopulated back to the ground state, both the ground state bleach will decay and the stimulated emission will also decay. And we are now actually after sort of formulating these two types of response. So when we take the rephasing diagram, we have to continue it now with the jump to the ground state. So we have precisely the process that we described above. From the rho EE, we go to rho GG. So we will denote this in our diagram in the following way. We will basically assume that there is some instantaneous process which brings me from EE to GG. And the next thing I'll do to continue the diagram will have to be interactions that correspond to the situation that we are now in the ground state. So instead of the decaying rho EE, I will have to put here into this pathway the term UGGEET. So along this time interval, I will evolve with the conditional probability that I started with EE and end up with GG. Now, the only question is how to continue this diagram. If you remember how the Liouville pathway diagrams were constructed, they always ended up with the EG pair of elements. So they ended like this, and then we had the process of emitting the field. Emitting the field meant that we contribute either to stimulated emission or actually also to the ground state bleach. So this diagram is still missing one arrow, but it's clear what arrow this will be. It has to be an arrow that comes here from the left and lifts the G to E. So this is the diagram that we obtain from the rephasing contribution that goes through the excited state. So this is in certain sense derived from the pathway R2, because the pathway R2 went to the excited state. But the problem is that the R2 pathway has a completely different set of interactions from left and right. So they have the same interactions at the beginning, so there is interaction from the right, then from the left, and then in the R2 we have interaction from the right and the emission from the left. So the last interaction is from the wrong side when it comes to the R2. And what is also very important, if you look at this pathway has an overall sign of minus. So overall sign which is minus, because it only has one interaction from the right hand side. So in fact this pathway, or in order to kind of identify this pathway, we would have to go to the set of pathways which have the minus sign, and those we always know that they are complex conjugated to some pathway which has a positive sign. So this will be either R1 star or R2 star or R3 star or R4 star. One of those pathways this is going to be. Before we identify the pathway, we will actually write down the other pathway we have to be looking for, because there is one pathway which starts as non-rephasing, or which is non-rephasing, and it also goes through the excited state. Non-rephasing pathways always start from the interactions on the left-hand side first. We will have to complete this with the right-hand side interaction in order to get to the E. And here we have the same situation. We will assume that there is a decay process with the probability U, G, G, E, E, T. And this brings us to the ground state. And the pathway has to be completed the way that we completed the earlier pathway. So we will have the arrow from the left-hand side and production of the signal. So this is basically the same situation as we described before, because also here we assume, or we see, that the overall pathway or overall sign of the pathway is minus. There's the same process, same sort of situation, having now non-rephasing pathway or contribution derived now from the R1 pathway. From R1 pathway. Okay, so I said that we will have to find the pathway, this non-rephasing and the rephasing pathway here, among the R1, R2, R3, R4, but star pathways. So these diagrams, the above diagrams, must correspond to R1 star, R2 star, R3 star, or R4 star. And that's because there is only a finite number of diagrams, of ways how you write the arrows from left and right. We have taken two of them, exactly half, which have positive sign, and we found that those have their image in the negative sign diagrams, and they only are complex conjugated of those. So when we find diagrams with minus, we have to definitely find them among these four possible pathways. It is not difficult to actually see that the first diagram here will be R1 star. The whole point is that the last arrow can be written from the left hand and right hand side. That is actually no problem. So we can ignore the last arrow or write it on whatever part we find actually useful, and that leads us to that identification. So if we denote this pathway here as pathway A, and this will be a pathway B, so we can do identification of pathway A, and now I can write the following. I'll write the R1 pathway. R1 pathway is non-rephasing, and it looks like this. Now when I put this under the star, so I complex conjugate it, I am getting the pathway with reversed order, or it's a pathway flipped along this axis here. So I write the interactions first from the right hand side, second from the left hand side, then there will be again left hand side interaction, the arrow goes in or out, that doesn't matter, and the last interaction can be written on the left or right hand side, and I will write it conventionally on the left hand side. I remind you that the last transition dipole moment operator in the construction of the response function comes from the trace. I'm tracing the perturbed density matrix with the transition dipole moment operator, and because one can rotate the operators under the trace, it can be written either as mu rho or rho mu. It doesn't matter, and that's why the last contribution comes from left or right equally. I'll write it, as I said, conventionally on the left hand side. Now what I had here under the star is the R1 pathway. In fact, we can check this on the B pathway, which started, I said this is the R1, so it has left, right, and then if we wouldn't go down to G, we would have to have the interaction on the right hand side, which will bring us to EG, and only then we'll get, by shining out the signal, we would get to GG. So one can actually relatively easily verify that this is in fact R1 pathway. That's what's inside here, and this is put under the star. So the pathway that we actually get altogether is the R1 star pathway. It's the R1 complex conjugated. And when it comes to identification of the pathway B, again of pathway B, it's quite similar. It's quite similar, and the identification will be with the pathway R2. R2 is rephasing pathway, and it has this composition when it comes to the occurrence of the arrows left and right. But if you put this under the star, which means flipping it, flipping makes non-rephasing pathway from the rephasing pathway, because the only difference is the sign of the phase, and in the diagram actually the order of interaction from the beginning of time. So we flip the rephasing pathway into non-rephasing one, we have the arrows organized like this now, and the last arrow can be put on the left or the right hand side, and I'll again conventionally put it to the left hand side, and whatever we have here in the brackets is actually R2 pathway, and that's why the thing here is R2 star. Actually, we also have to write and stress that again, if R1, the response, is defined with the positive sign, then the diagram here is minus R1 and minus R2. Okay, so that is the identification of the pathways by which we describe the contribution of the relaxation of the population of the excited state to the ground state. So we can now write down a summary of all the Liouville pathways which contribute to the pump probe experiment or nonlinear response of the two-level system with relaxation. So we have a summary of Liouville pathways for relaxing two-level system. And the list, I will not just do a list, I will actually write out how the response functions in our definitions look like. So we have R1 T, capital T, tau. The prefactor to everything will depend on the fourth power of the transition dipole moment. I will write it now like this, but we have to bear in mind that this prefactor is a little bit more complicated by the fact that it contains or consists from the projections of the transition dipole moment vectors on the polarization vectors of the fields that shine on the particular molecule. The thing is that the response is supposed to be microscopic, a sum over many molecules in the sample. So this prefactor will have to also include an averaging over all possible orientations of the transition dipole moment. And we will actually consider this averaging exactly in some of the next videos. However, here we'll write without thinking much this d to the fourth power prefactor. Because in fact, for this very simple case of the two-level system, this will truly be just a scalar prefactor with some maybe 1/5 or something like that. So the response functions contain now the evolution superoperator elements corresponding to the ground state and excited states, and of course coherences between them, and we will put them in here based on the diagrams. So for that you actually have to go back to the list of pathways that we have so far and look at the individual diagrams at the intervals t, capital T and tau. I will not do that explicitly here, I'm only listing the result. So we will have here for the third interval EG, EGT, that's basically always the contribution, if I may then, at least in this case, that's the last interval here with the T, that's the last interval contributing. From EG we go to EG. Then before that there is an evolution of EE that depends on the capital T, and here we consider in the R1 pathway, we only consider the evolution from EE to EE. Then the next step or the last interval is EG, EG again, depending on tau, and that's because R1 is a non-rephasing pathway. If we look at the standard non-rephasing pathway, we have EG in the tau interval. Well, here we have EE to GG, but that's the T interval in which in the standard R1 nothing happens, and then we have, as we already said, the EG again. That's the non-rephasing pathway R1. For R2, which is rephasing, we have basically the same thing. We have D4, we have EG, EGT. This part of the response is always the same. We also go through the excited state, but we have an opposite direction phase factors in here. We have the coherence GE in the rephasing pathway. That's here the pathway A, the one which we identified as minus R1 star, is rephasing, and it has a GE interval in the time tau. So this is R1, R2, but we also have R3, T, R4, T, capital T tau, and we have R1 star contributing, and we have R2 star contributing. So that means we can now write the rest. The R3 and R4 are the pathways that go through the ground state. So we have this, and R3 is rephasing, so it has GE tau. Then D4 is non-rephasing, going through the ground state, so it has to look like this. These are capital T's, and it's a non-rephasing pathway, so it has to have the same phase or same direction of the oscillation as the last interval, so there must be EG tau here. Now R1 also has the D4, and R2 also has the D4 prefactor, and they of course have to end up with the same conventional evolution superoperator element, so the dependence on T is the same. But here in R1 we have energy transfer from excited state to the ground state, the same in the R2 star. And the difference is that R1 star is rephasing, so it has GE tau, whereas R2 star is non-rephasing, so it has EG tau. Okay, so this is it. This is basically the list of response functions that will enter the calculation of the pump probe experiment or pump probe spectrum of the two-level system with relaxation from the excited state to the ground state. So let's now describe the pump probe. We already have everything in our hands. So pump probe experiment, the differential absorption experiment, will give us the following. The dA, the differential absorption, should be in the impulsive limit, that is when the pulses are extremely short. It will look, or it will be proportional to, that's maybe better, it will be proportional to minus omega, the minus sign we have discussed. The omega comes from the omega that sits in front of the polarization. That's what comes from the Maxwell equations. And then we take real part of the, normally there would be an integral of the response functions with the fields, but the field have been integrated already because they are ultra fast, they are delta functions, so there will be only their amplitudes. And we divide the definition of delta E, we divide by the amplitudes. All right, they can be also, the dependence can be left there, no problem. We have proportionality here, so we will not write the amplitudes, and but we have to write the response functions. And we know that because this is a omega dependent function, we have already introduced how we actually detect the omega Fourier transform, the spectrum of the response function in the time t. So there will be R1 omega, which is the Fourier transformed response function, R1 above, it depends on tau, and we have Fourier transformed that into omega. So then the rest of the dependence will be on capital T, and in the impulsive pump probe, tau will be equal to 0. So we have R1 plus R2 plus R3 plus R4. Of course, in all cases, they will be Fourier transformed and tau will always be 0, etc. And then we have minus R1 star minus R2 star. And that's how the definition actually ends. That's the differential absorption. If we want to know how the differential absorption looks at the time capital T equals 0. That's a very important situation. That's basically when the probe pulse comes immediately after pump. It must be so quick that basically nothing happens. We will get minus omega d to the fourth power, real part of, and now of what? Well, if you look at the pathways, when capital T is equal to 0, then the elements of the corresponding evolution superoperator will be either 1 or 0. In this case, the ones which have all indices the same, like this one here, will be 0, and the ones which have a change in the indices, they will have 0. So here we can assume, and of course the tau is equal to 0, so this is also contributing with 1. So we only have here the first of these two elements, and this we have already, or its Fourier transform we have already identified with some sort of a line shape, but it's a complex line shape now, and the real part of it actually makes an absorption line shape out of that. So what we get here will be always the Fourier transform of the u, e, g, e, g, t. So Fourier transform of this will be called g, e, g, omega. This is something that we assume here, something that we have discussed before already, and now we use it in this expression. So we write g, e, g of omega plus g, e, g of omega plus once again g, e, g omega and g, e, g omega. 4 terms which come from R1, this one come from R2, etc. Plus, of course, or minus 2 zeros which come from R1 star and R2 star. So this is how the response function or the pump probe experiment will look like at t equal 0, and we can write this even better. So there's equal minus omega 4 times d to the fourth power, and here absorption, really absorption spectrum of E, G, omega. Well, here maybe a better definition would be without omega here, because as you know, the absorption spectrum also contains an omega prefactor. So this is, well, to be sure, really this is also just proportional. But the important conclusion here is that the differential absorption will exactly copy the standard absorption. So there will simply be a less absorption in this two-level case at t equal 0. Now we can of course write down the differential absorption also at general times t, and then we are getting minus omega d4 and real part of. And now let's have a look at the contributions of u, e, 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 and u, g, 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 and u, g, g, e, e. So we write it all out here. So first two contributions come from R1 and R2. These are standard Liouville pathways going through the excited state. So there will be twice the same contribution, but always with minus K, G, E, capital T, because that's how basically the U, E, 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 E contributes. Then we add two static contributions, G, E, G, omega plus G, E, G, omega. There is a 1 here, and that 1 comes from U, G, 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 T. And then there is a contribution which comes from the R2 star and R1 star, which has a minus sign here. So this is minus, again, G, E, G, omega plus G, E, G, omega. They have the same contribution, and here we have 1 minus e to the power of minus GEG capital T, and this thing here is the contribution of UGGEE capital T. Okay, we can close this bracket here, and this is the full expression for the differential absorption. We can actually go and cut some of the contributions, because clearly the contribution here with 1 will cancel this contribution here, and as a result we see that we have, there's a minus, so that's plus. We can see that delta A of T actually looks like something that is overall decaying with the factor e to the power of minus KEGT. So we have 4 times GEG omega e to the power of minus KGE capital T. So that's a very interesting result, which of course gives us the useful and maybe expected fact that the delta E, when t goes to infinity, must in fact go to 0. So clearly, if I draw the delta A as a function of omega and look at its time evolution, I can see that first I have some sort of a maximum drop of absorption with respect to the standard absorption. So we have a negative contribution, which then actually starts to decay as the time capital T goes up. And that is because if you look at the actual absorption by the probe, this is omega, and this is not delta E but delta A, but A of the probe, we see that initially, so this would be the standard absorption without pump, and here we would have the initial absorption at T equal 0 after the pump. There is this missing absorption here, which will actually slowly, as the time progresses, refill, and at very long time we will have exactly the same absorption as if no pump occurs. And that's because the fact that we have excited the system by the pump pulse gets forgotten. Everything that has been excited decays to the ground state. So we can observe, that's very important, if you make a cut of this spectrum along one of the frequency and draw the dependence of delta A at certain omega as a function of capital T, what you should see is, in this particular case, an exponential decay as e to the power of minus KGE T, and therefore pump probe allows us to observe the dynamics, the kinetics. Actually, it allows us to measure the relaxation rate. So pump probe can measure, well, it not only measures it, but it really observes in time the process of decay. It can measure relaxation rate, KGE. In order to get closer to the description of realistic systems, we have to consider one more very important experimental fact, and that is that two-level molecules do not exist, in fact. Whenever I have ground and excited state and I shoot with the laser of the frequency omega to the system which is already excited, I can be almost sure that somewhere in the vicinity of the same transition I will get another state. It doesn't have to be exactly the same transition, it can be somewhere else, it can be way more levels than just one, but I have to assume that there are transition frequencies omega EG and transition frequencies omega FE, for which we can see the process of so-called process of excited state absorption. My system is in the excited state, and by shining light on it, it still absorbs because it excites farther to a higher excited state. So we have to figure out what pathways describe the process of excited state absorption. Excited state absorption, or ESA, a process very important in nonlinear spectroscopy in general. Liouville pathways that describe excited state absorption have to be based again on those Liouville pathways that go through the excited state. So we can again, because we know that we have two of them, we have one rephasing and one non-rephasing pathway, we can again build a rephasing pathway through the excited state, which will continue towards the excited state absorption, and a non-rephasing pathway that does the same. So here we have different orders of excitation. Now, obviously, when the excited state is decaying, this pathway will also decay. So the only contribution in time t here is again the UEE EET, nothing else. Because the processes by which we get to the higher excited state, or by which we induce further absorption, they will be also induced just by light. And now we have to think clearly what we need. We actually need to close this pathway so that we can put the signal here. Again, we have to have a signal that corresponds to an optical coherence. But what states will be involved now? It has to be, in order for this to be a signal that we can detect, it has to again have a dependence that looks like minus I omega, which will be the frequency of the signal t. But if you look at the diagram, and if you excite twice to the excited state and then to the F state, the only way how we can get a signal that occurs around the frequency omega is from the coherence Fe. So here we will have to assume the Fe frequency, and therefore we would need the last interval to look like Fe. And actually we don't need to have here this line at all. So it has to be Fe. How do we get to Fe? Only by an additional action from the right hand side. So we can see that the rephasing pathway again contains an overall sign minus. This is the overall sign minus because it only has one interaction from the right hand side, and because it's a rephasing pathway, it has the first interval of e to the power of I omega Eg tau. When it comes to the non-rephasing pathway, the end of everything has to be basically exactly the same. We go to Fe, and then we shine the Fe signal. So here e to the power of minus I omega Fet. But in the first interval, we have e to the power of minus I omega Eg tau. That's the non-rephasing contribution. And clearly we can again go and identify what diagram this is. We find again that this is the R1 star diagram, and here is R2 star diagram. Again, the sign of this contribution, even the sign of the R2 contribution, is minus. So very nice. We have now a signal which occurs on a different frequency than the one from the ground to the excited state, because we possibly have a different location of the excited state. It doesn't have to be double the frequency of the transition G to E. So we have possibly a richer differential absorption for the three-level system. And assuming that we have here, somewhere here, the frequency omega Eg, and for instance we have a higher frequency omega Fe, we could easily see that because the absorption, excited state absorption at the frequency omega Fe has a minus sign, so it contributes more absorption. The response has a minus sign, but the overall delta E has yet another minus sign in front of the response function. So all positive response functions contribute with less absorption, minus. That's what we already have seen for the two-level system. So we will have something like this here. And the excited state absorption has to contribute with more absorption. So it would contribute like this. So here in this system, we now have the contributions of ground state bleach and stimulated emission. Those contribute with less absorption, and the excited state absorption, which contributes with more absorption. In a situation that, for instance, the two transitions are very close to each other, EG, and right next to it we have FE, we would get sort of strange line shape which would cut both of these. So here on the left hand side diagram we see that the width of the spectra is such that the spectra would go close to zero anyway in the middle between omega EG and FE, but here they sort of cut each other and have a sort of characteristic line shape with a nodal line. So for instance, in this case of the omega EG and omega FE closer than the width of the transition, we cannot actually guess the width of the transition in pump probe. The width of the transition is partially influenced by the cancellation of the signals. It is important to say that both excited state absorption and stimulated emission decay directly with e to the power of minus kGET, whereas the ground state bleach remains the same, but we also have a contribution of refilling the ground state bleach, and even in this case all the signal at t equal infinity would go to zero. It's important basically as an additional information during decay of the state E, also excited state absorption decays. So it decays as e to the power of minus kGE capital T. All right, so now we have considered essentially everything there is to consider when it comes to the processes. We have ground state bleach, excited state absorption, stimulated emission, and the process that refills the ground state bleach and kills excited state absorption and stimulated emission. Now we will have to generalize these processes and their description to a general multi-level system. By a general multi-level system, we actually usually mean a system of three bands. So we have ground state as the sort of singular band with one state, and a band of excited states, which we can label, for instance, by state 1 to n, and then a band of higher lying states which occur at about twice the frequency of the transition from the ground state to the first band of excited states. So here we have set number of states in both bands, and for the states to have any relevance there has to be an allowed transition from ground state to the first band and then from the first band to the second band. If there are any states that would occur somewhere in between, they might or might not actually play any role depending on whether there are channels, for instance, for these states to be populated from the doubly excited state or higher excited states, or for instance whether there is a chance that these states will decay further to the singly excited states. However, for instance, importance of the processes from the F1 state, for instance, here to some state that lies in between the band states is actually quite limited, because we never reach a state within our perturbation theory, nonlinear perturbation theory, as a response to the external light. We never reach the evolution superoperator elements that would correspond to the population of the F1 states or F2 states or any of the higher excited states. And therefore, the relaxation does not contribute directly to the signal. It can only effectively increase the dephasing rate of the coherence between the first excited state band and the second band of excited state. So it will contribute to the width of the excited state absorption and nothing else. So it is important for us to understand how one can calculate the spectrum of such a multi-level system. So imagine that we know all the processes that occur between the states of the first exciton band. We know order or first excited state band. We know also the similar processes in the higher excited states. This basically, exactly as the relaxation to an intermediate state, will only lead to a broadening of the states, but we need to know all these things in order to be able to write all the elements of the evolution superoperator, and then we can construct Liouville pathways in this kind of system and sum over all of their contributions. So we might have, for instance, energy relaxation pathways, in which we excite first to some state. For instance, this would be a rephasing contribution or rephasing Liouville pathways, where we first excite to state n, then we propagate from state n to state m, and that takes the time t, and then we have a m, state mg and mg coherence, and this means here dn square and dm square as the prefactor. Roughly, this is going to be a contribution for the state n, and we have to sum over all states n and all states m into which we could possibly relax. So we have to sum over all energy relaxation pathways, over all types of them. So for instance, what I have written here would be a pathway that is rephasing going through the excited states. So this is going to be something like the R2 pathway or R2 pathways, because you can see that we have to go, or we can go through any of the states of the first exciton band. We, for instance, also have coherence decay pathways, which could be constructed in a very similar way. So we again excite to some state, which can be n. We first excite into state n and propagate its coherence. Then we excite to a state m, so that we create a coherence mn in the excited state. So this is going to look like this: m, n, m, n, t. And then we can end up, for instance, again in the state, no, it has to be m in this case, m, g, m, g, t, and that would mean that the first excitation was into n, the second was into m, then there has to be de-excitation in n, and the last one is de-excitation or emission in m. So this would be a coherence contribution, and again we have to sum over all m's and n's. So there's going to be a really large number of individual Liouville pathways based on how many ways or how we could actually put together the elements of the evolution superoperator. Now, the evolution superoperator for this middle interval of the length t according to a secular approximation, always has this form that we start with nn and end up with mm, or we start with nm and end up again in nm. So these are the only allowed contributions that we have in secular approximation. So we assume secular approximation. And similarly, we also assume secular approximation for all states that contribute to excited state absorption, which contain elements, for instance, F, N, K, F, N, K in T. And that is the coherence between one of the higher excited states and this first band. This contributes or goes into ESA signal. All right, so we can somehow summarize and give basically at this moment an advice or a recipe of how to calculate spectra, and not only nonlinear spectra like pump probe, but also, for instance, the absorption. We will write down also the expression for repeat the expression for absorption, because we see that pump probe, etc., can be written using certain definitions that occur in the absorption definition. So we can basically express the pump probe using the absorption line shape. So the question is how to calculate spectra. The first spectrum we want to calculate is the absorption spectrum. And let's think in terms of this multi-level system. So absorption, because it's a linear method, it will never reach, let's assume we look for the absorption in the region of frequencies where we go from the ground state to the first excited state band. And in that case, we do not have a contribution of the doubly excited or higher excited states, because we only have one action of the field which can at maximum bring us from the ground state to the first excited state. And the absorption spectrum up to quite unimportant prefactors is proportional to omega, sum over all the states in this first band of states. We have the real part of the absorption of the absorption line shape. This is a function which I will show how it looks like. But this function, the real part of the G, gives basically the line shape of the transition from ground state to the excited state N. And we expect here transitional dipole moment Ng to occur as a square. But that's not all. Let's say we would excite by polarized light. If we excite by polarized light or absorb polarized light, the molecules, however, molecules in the sample, they have different orientations of their transition dipole moment with respect to this polarization, and namely they have all thinkable orientation. So we have to average the projection of the polarization of light on the direction of the transition dipole moment of the molecule over isotropic distribution of directions. One thing is, it's clear that if we don't do the excitation with polarized light and we use unpolarized light, it shouldn't matter. In fact, it shouldn't matter at all, because we still have to average over all possible orientations of the molecules. So we don't just have d and g squared, which would mean that there's a transition dipole moment of the molecule squared, that is its length, but it's an average over the projection. So we in fact have something like this. We have this g here and the polarization of the exciting field, and we average square of this over all orientations of the transition dipole moment d and in space. So clearly this is something we still don't know, and therefore this recipe should work up to the calculation of this average, and the average will be actually a subject of our investigation relatively soon. Now we have to complete this with some definitions. So G and G omega is a Fourier transform, regular Fourier transform of the element of the evolution superoperator. It's the element with ng, and it's the element with a jump function here. So we only assume positive times t. It's an actual Fourier transform, so it looks like this. So in fact, if we go into details, this is going to be an integral from 0 to infinity, and we can also think about writing the ng and gu and g using the slow component of it and the main contribution to the oscillations, which is the frequency omega and g, the transition frequency, and a Fourier transform. So this definition we have to keep in mind, because we will also need it in definition or in the recipe for calculating the pump probe spectrum. So let's have this as an important result, and let's go to have a look at the pump probe spectra. Pump probe spectrum. Now this is more complicated, but we also already have all the ingredients except the average over the contribution of different orientations of the transition dipole moment. So let's write it explicitly out what we have. We have delta A omega proportional to minus omega, that stands over everything. And now we have a sum over all possible combinations of states. And in fact, I'll first write the transition dipole moments here. So the transition dipole moments, there will be 4 of them, and they are always between ground state and a certain excited state. So we can label the states, the excited state, with, for instance, indices k, l, and m. So this will be g to k, l to g, n to g, and m to g. In fact, the order in which I write the indices is not that important, but we have also the pulses and the polarizations of the pulses, and they will go here from the right. So this will be the first pulse, second pulse, third pulse, and the local oscillator. These scalar products have to be averaged over all the possible orientations of the molecules. And because you see we have k, l, and m indices, so we also have to sum here over n, m, k, l. And now this we will multiply by real part. If you remember, the differential absorption is a real part of the response functions. And now we always have the pair of rephasing and non-rephasing functions, non-rephasing response functions. And because tau is equal 0, the first interval between the pulses is equal 0, we are in pump probe. There is no difference between rephasing and non-rephasing. So we always have a factor of 2 in play here, because we sum rephasing and non-rephasing pathways. We have such pathways that go through the excited state. We, for instance, start with an m and end up with KL. That corresponds to the transition dipole moments here, and this element depends on capital T. And let's say, well, we know that this can only be the coherence or population evolution. So we have certain possible conditions on the allowed values of the indices nm and kl. So for instance, we know that n has to be equal m, and once that is true, K has to be equal L. Or when n is not equal m, which is that because when 1 minus delta n m is non-zero, we will have delta k n, that is k index has to be equal to m n, and delta l m, because L index has to be the same as m. So in this case, in both of these cases, we end up with, so if we go through the excited state, we excite into states m n, and then we end up at the end with the states k l. And here we, for instance, we have to get rid of the index L because in the pathways we know that the last element, the one depending on t, is always certain state and the ground state, so kg. The origin of this term is from the Fourier transform of u kg kg of t. Yeah, that's how we get there. Okay, this is the contribution of the stimulated emission, and in stimulated emission we have energy transfer. We also have the situation in which nothing transfers, so it's like, for instance, nn to nn. That can also happen here. And we also have coherence contribution, in which we excite coherence in the excited state, so the non-diagonal, off-diagonal element of the density matrix, and it gets propagated according to the secular approximation. All that is inside this equation that we have just written. So that's the excited state absorption. And there is also, obviously, with a 2, there is a ground state bleach contribution, which should look very similar, except that the middle interval is u g g g g and nothing else. In that case, the first 2 transition dipole moments are always the same, because there is a transition from g to m and then from m to g. So we have to have a delta n m, and we also have to have, therefore, once we start from the ground state, we also have the second 2 contributions of the transition dipole moments the same, so delta k l has to stand here, and this is the ground state bleach contribution, which is one of those constant contributions. In fact, here we can see that this is the R2 plus R1 pathways, and this is R3 plus R4 pathways. That's not all. We also can have a contribution in which if the excited state decays, we can have also this decay contribution, which will have an opposite sign. So we have minus 2, again, GKG, for the same reason as in the first term. This is basically Fourier transform of the UKG KG, just to make sure this is really KG KG. Okay, and here we have UGG and N. T, that's the decay to the ground state, if any, and delta N M delta K L. We should not forget that we still sum over N M and K L. So whenever we write something that has only an N M index, for instance, or N index, we have to also fill in the rest of the indices. So here I will close this contribution, but it's not yet all of it. So this term here is the ground state bleach filling. That's the pathways R1 star and R2 star, but those with relaxation. I mean the relaxation to the ground state. But we still have another contribution, and namely the contribution which goes to the higher excited state, that is the excited state absorption, and that one has a plus sign, overall plus sign in the sign convention that we use here, and it has to have, well, it will have basically all the necessary states that we had earlier, so we excite to states. And M, we can, in fact, when this is two states the same, like N, we can transfer to, for instance, KK, and then we can have a transition to a certain F state. So we have to sum over N, M, F state, and K and L to be actually complete. And the factor that we have to average over is again containing 4 transition dipole moments. The first transition dipole moment will be mg, and it's in a scalar product with the polarization of the first pulse. Then we have ng and the second pulse, and then we had third pulse, and here this is going to be from some general state K to F, and then from F to K. So these are all the transitions over which we have to average. Now here we probably should have, to be consistent, G M. Okay, and behind this we hide a factor 2 real parts and the response function corresponding to the excited state absorption with the first interval Fourier transformed. So this is going to be Fk, like we had before, the Kg, so that this has a certain phase factor, namely the e to the power of minus I omega k g t. So here we would have Fg. So the first one is the state with the higher energy and of omega, and behind that we have U, K, L, and M, but with capital T. And now the conditions are that either N equals M and then also K equals L, or when that is not true, we have K equal N and L equal M. So you see that we actually need all the indices that we need here in the sum. Okay, and this is the excited state absorption contribution. Now this should be really all there is in the pump probe spectrum. We have used approximation that might not always be valid. For instance, we always assume ultra short pulses and tau equal 0. Our line shapes G, K, G don't really look very realistic because they only are Lorentzian line shape, but nevertheless most of the processes that we expect to happen in molecular systems, they are inside in here in these expressions. It's a bit lengthy, but if you have a computer, you could relatively easily calculate absorption, the transient absorption spectrum now. Or could you? Well, because we still do not have those averages over the orientations of the molecules in space. So one option would be, for instance, because these calculations, although there are some big sums here and so on, they are not that expensive. So in principle, you can try to take your system, define your system in space, and then rotate it by some approximations over random Euler angles, and in fact really average the values of these dipole moment prefactors and insert them numerically into your calculation. This sounds like it's quite practical. However, there is one more practical way, which works perfectly when we can assume that the molecules are distributed in the sample isotropically. With the isotropic distribution, one can actually calculate all these averages exactly, and that's what we will do now. It may sound a little bit improbable, but those rotational averages over the transition dipole moments for an isotropic distribution can be really calculated in a quite easy way analytically. So you probably expect a lot of integration over many Euler angles and so on. Nothing like that is true. The argument is not that difficult as it might also first sound. So trust me, we can calculate those averages analytically in a very general way. So what's actually the problem? Let's have a look first. What's the problem? So we have light coming to a sample of molecules along some k vector, and orthogonal to that k vector we have a polarization vector of light. So this is the E, and when this finds molecules in the sample, they are each, or let's say they are two-level systems with one transition dipole moment, but in general they are all oriented perfectly randomly in the area, which can be considered actually one point of our sample from a macroscopic point of view. And if you remember, in all our expressions for the interaction between light and matter, we always have mu E. So this is an operator which is for the given transition. We always postulate a transition dipole moment, which is a vector which meets here with the electric field. And this can be written using the length of the transition dipole moment and the amplitude of the electric field, and then using let's say a unity vector n along the direction of the d and the polarization vector of the electric field, which is also a unity vector. Now, the way that I draw it, everything is fixed in space, or is defined in space. The vector E is definitely something which is fixed in the laboratory frame of reference. It's and this is really fixed in the experiment. We don't do anything with it. What about the n? Well, n of course can also be easily defined in the laboratory frame, but because it is different for each molecule, so different for each molecule, the characteristic n, the characteristic direction of n, especially when there are more transitions, is always better defined in the molecular frame of reference. So we will assume that this is defined in the molecular So in fact we can specify just one direction, and this is meant to be a representative of all possible directions of the molecules, because we will rotate that original vector, and we assume isotropic distribution of directions. So for instance, if we take the vector n and a single vector and rotate it in all possible directions, so that we make an average, and those vectors make an average of the direction, we get 0. That's basically the condition of that distribution being isotropic. The first problem that we have is how to calculate the corresponding contribution of the transition dipole moments, or the averaged transition dipole moments, to absorption spectrum. So the first problem that we have is how it works in the absorption. So in the absorption, we also again assume secular approximation. So in secular approximation, we only have the following expression. We only have basically, no matter how many transitions we have, each expression always contains a single transition dipole moment twice. So we only have this situation, and here we average over all directions. And it would be, of course, it's then clear that we have d square, where this is the absolute value that is the length of the transition dipole moment, and here we average over n e square. Okay, so this should be easy. This should be easy, and we will demonstrate on this example how these averages could be calculated. But the more difficult problem is in pump probe. That is a pump probe and other non-linear spectra. Here we have a more difficult problem, which in the third order would look like this. It would be an average over some d4, e4, d3, e3, d2, e2, d1, e1. So 4 of them averaged over all possible orientations. That would mean d1, d2, d3, d4, that is their length, and then an average over n4, e4, n3, e3, n2, e2, and n1, e1. So we average over products, scalar products of vectors of unit length. So in principle, in pump probe, we have 4 different possible polarizations. We have E1, E2, E3 of the first, second, and third pulse, and then we have E of local oscillator, and they are again fixed in space, although they can be basically whatever. And then we have 4 different orientations of the transition dipole moments, and they are fixed only mutually fixed, but arbitrarily rotated. And all this we have to take into account in our calculations. All right, let's then start with the case A, which is the case of absorption. Well, let's do the following. We write again our task, and we write it generally. So although we can assume that they are same, we will not do that. So if we write this out explicitly, it's d1, d2. By this I mean the length of the vector d1 and vector d2. Here we have n1, e1, and 2, e2. This can be written now using the definition of the scalar product. So d1, d2 we sum over index I and over index j, and we have the n1 I e 1 I, that's the first scalar product, and the second product is n2j e2j. The indices that distinguish the two different vectors, 1 and 2, I have moved them now up, and the lower indices are the xyz components of these vectors. All right, and now I rewrite this once more in the following way: d1, d2, I keep here I and j, and I write together the e1i and e2j, and I write n1i and n2j together. And now it will be very interesting to realize that this quantity is actually a tensor. This is a tensor. It has two indices, and well, what is it a tensor? Tensor is something that under the transformation of coordinates transforms in a particular way. And that's exactly what this does. It's a quantity that because it consists of a product of two vectors, you can always transform those vectors, and that's how a tensor transforms. So this is definitely a tensor. Now if I assume the average over all possible rotations of this, I get d1, d2 sum over ij e 1i e2j, and here this is the only thing that depends on the orientation. So this is the average over the tensor I have defined or identified above. Okay, interestingly, this tensor, because it is already averaged over all possible orientations, it cannot change under a rotation. So if I take this tensor, the tensor which I get by averaging over the tensor one line above, this tensor cannot depend on a rotation. A transformation of indices ij, transformation of bases, transformation in these indices, cannot change it. So which tensor does not change under the transformation of coordinates? So if I take a tensor ij and I transform it to a different set of coordinates, so I apply a matrix, transformation matrix S on it. So this is going to look like this from both sides. JL, in fact here on the left hand side this should be S inverse, and we have to add J here. So only if A is a multiple of unity matrix, then it stays in its form exactly the same under any transformation. We can verify that easily. This is A ij s minus 1 ki, and here we have ij s j l, and that gives us actually s minus here k I s I l, and we still sum over I, and that, because this is an inverse matrix to S, this has to give delta k l, and we forgot the A here. Okay, so the matrix, which is a multiple of diagonal of is diagonal, it's a multiple of the unity matrix, does not change under the change of coordinates. So in fact, we have to expect that this expression INJ2 is going to be a multiple of IJ. All right, that's true, but because we have this thing expressed in the laboratory frame, and that's not a convenient frame, we can re-express this thing, or we have to re-express this tensor now in a way in which we can define the molecules, and that's only the molecular frame. So we have to add to our expressions here one more transformation, and then we have to think again what possibly this the results that we got here, this one, what does it mean for our task? Okay, so let's see again. We write D1 E1 D2 E2. So how we can write it? Now using the fact, or using the molecular frame. So here we have an expression I1 EJ2, and we want to write the expression here, which is in laboratory frame. We want to write it using the frame of reference bound to the molecule, and each molecule has a different relation between its molecular frame and the laboratory frame. So we assume that we can in fact always write the Ni using a transformation from the molecular frame. So we have the Ti, and I will use alpha for the indices in the molecular frame, and here I have the J, the same transformation, beta and 2 beta, and of course this thing now has only a certain part which is dependent on that transformation, on the rotations. So of course here this is omega, and here we write D1 D2 sum IJ E I1 EJ2, and now here we have N alpha 1 and beta 2, which does not depend on the rotations, but we have a part which does, and that's the Ti alpha Tj beta, and that is averaged over all possible orientations, and we will denote this as it's a tensor transformation. It transforms from two indices alpha beta to two indices ij. So it's ij alpha beta. And this is a thing which is averaged over all possible orientations. Well, we still forgot, sorry to add that late, but here we also have to sum over alpha and beta. So here we add these sums over alpha and beta. So when we sum over alpha and beta, that's when we do this transformation from alpha beta to ij. And in ij, I know that the result has to be proportional to delta ij. So I know that ij alpha beta has to be maybe some value a, but here delta ij, and the rest I don't know. It has to be proportional to delta ij. So I might assume, for instance, that there is something else. Now, how do we find out what that rest is, or how can we actually hope to work with this? We can again have a look at some things that get conserved under the rotations, And for instance, with the tensor that we have here, what gets always conserved are things like scalar products between two vectors. So for instance, I can assume that something like n1i and 2i, which is a scalar product of two vectors, remains constant under all possible rotations or transformations, even the transformations that are mediated by this tensor ij alpha beta. So I can write for this constant here, for instance, this sum over I, sum over alpha beta, I have actually, I'm transforming this or writing this using a transform from alpha and n1 and 2 alpha beta. So this is how it can be written. This is quite clear, because the ij alpha beta transforms from the molecular frame of reference, and I have expressed this thing now in the molecular frame of reference. But I also know that because this is a scalar product, the constant is the same in all possible reference frames. So this must also be alpha sum over alpha and 2 alpha. The same constant, clearly. So now that means for instance this, I can actually take this second part of the expression and write it the following way: sum over alpha, sum over beta, sum over I, sorry, I forgot alpha beta here, I alpha beta n beta 2 minus, then I take this expression from the right hand side and put it on the left hand side of the equal sign. So I get here n alpha 2 and multiply by n1 alpha, and that equals to 0. Because of the equal sign here, I can also write this, and this has to be 0 actually for any variant of n. I mean, it's arbitrary of my particular case of those vectors. So that means that whatever I have here in this bracket has to be 0. So this is also 0. And what is it here? Here I have something which is actually a sum over my indices I. So it's a tensor with two indices alpha beta. So I'll call it kappa alpha beta, and my equation now reads sum over beta kappa alpha beta n beta 2 equals to n alpha 2. Well, that can only happen when this is delta alpha beta. So I have just found that sum over I alpha beta equals delta alpha beta. Now I look up here where I saw that I don't know how the ij alpha beta depends on alpha beta, but I know that it depends as delta ij on the ij, and there is a before. So I can actually assume, or I'm drawn to a conclusion, that ij alpha beta is going to be a constant, and then delta ij delta alpha beta. And because when I sum it over the two indices the same, we contract basically the tensor, and it has to give delta alpha beta, I get delta alpha beta equals delta alpha beta. But because this sum gives 3, so it's 3 times a delta alpha beta equals delta alpha beta, and that gives me a equal 1/3. All right, and that gives me my important result, that the ij alpha beta equals 1/3 delta ij delta alpha beta. And with this result I can go into the transformation and I can finally perform it. So I can calculate what was my original task. E1, D2, E2. Now I put everything I have together here. It has to be D1, D2, sum over ij alpha beta. Here is E1, E2, and here in the middle I will have 1/3 delta ij delta alpha beta, and here I have n alpha 1 n beta 2. This is also 1 1, and in fact this is I and j. Sorry for the confusion. Okay, now this is D1, D2, and we can see that we can leave only I and alpha. So there is E1 I, E2 I, scalar product of the polarization directions, but that is already because there's only one field or one direction. Well, okay, let's leave it like this. Let's write the general result. So 1/3 can be put in here, and here we have n alpha 1 n alpha 2. So what we have is D1 D2 over the third, and here we have E1 in a scalar product with E2 and N1 in a scalar product with N2. Nice. Interesting thing is, of course, that in absorption spectroscopy there is always E1 equals E2. So the expression in general looks like this, and it is therefore D1 D2 divided by 3, and there is a product of the two transition dipole moments, or directions of the two transition dipole moment. And because we have everything in secular approximation, the usual expression for the absorption only contains something like this: the transition to the nth state to the squared averaged over omega is the length of the dn square divided by 3. So that is what we got for the absorption. And in a very similar way, we can also derive the expressions for the corresponding terms with 4 transition dipole moments. I will do it in a separate video, which is not needed in order to follow the rest of the lecture, but we will actually derive all these things, and we derive a technique by which you can calculate for any Liouville pathway, that is any combination of the transition dipole moments, the corresponding prefactor. As I said, it's not something that is needed for the rest of the lecture, but there will be some quite important terms like magic angle and so on explained there. So for the sort of practical use of pump probe spectroscopy and similar spectroscopies, it makes really sense that you see all those things. But otherwise, the video will basically be a bonus video.